Put your hand in front of a speaker playing a low note. Why don't you feel a steady wind if sound travels through the air? Because that sentence hides a trap. The words "travels through the air" make your brain picture air, leaving the speaker and arriving at your ear, like a little invisible breeze with musical talent. And yet, in front of a speaker, you don't feel a continuous stream of air pouring out. You feel a trembling, a push, then a pull, then a push again. The air isn't marching from the speaker to you. It's mostly rocking back and forth in place. So what is it that actually travels? Most physics books show sound as a neat sine wave sliding across the page. That picture is useful, but it's also the reason so many people secretly misunderstand what sound is. The drawing looks like a rope wiggling up and down, moving through space, and your brain quietly decides the medium must be doing that shape. The air must be making a wavy path. But air doesn't have an up and down in a sound wave the way a rope does. Sound in air is mostly a squeezing and relaxing, a pressure pattern that moves. Let's build the real picture from the ground up, the way you'd do it if you had no textbook at all, just your senses, a few experiments, and a stubborn refusal to accept magic words as explanations. Start with the simplest experience. Clap your hands. You hear a sharp sound. Now ask, what physically happened in the air between your hands and your ear? Your hands came together and shoved the air. Not as a steady shove, but as a sudden compression. That compression created a region where the air molecules were for a moment closer together than normal. And air does not like being squeezed. It pushes back. That push causes neighboring air to get squeezed, and then that neighbor pushes on its neighbor, and so on. The pushback moves outward. That's the traveling part. But the empty molecules themselves, most of them don't travel far at all. If you doubt it, do a thought experiment. Imagine a concert speaker blasting sound toward you. If sound were literally a flow of air from the speaker to your face, the region near the speaker would be constantly losing air, and the region near you would be constantly gaining it. After a while, you'd have a problem. The front row would be drowning in extra air, and the stage would be in a vacuum. That doesn't happen. The air isn't being transported. The disturbance is. That's the first big shift in your understanding. The air is the messenger, but the message is not a packet of air. It's an organized pattern in the air's pressure and motion. Now, if we want to be honest, we have to admit something. The words organized pattern can sound poetic. So let's be mechanical about it. What exactly is changing point by point in the air? There are three main things you can talk about, and they're all tied together. One is how much a tiny chunk of air has been displaced from its usual position. Imagine the air divided into little parcels. When sound passes, each parcel moves a little forward and back along the direction the sound travels. Second is density. How many molecules per cubic centimeter at that location compared to normal? Third is pressure. How hard the molecules are banging on the walls of an imaginary tiny box at that point. You might think these are three separate stories, but sound is basically the dance among these three variables. A pressure difference causes acceleration. That's just Newton. If the pressure is higher on the left side of a little parcel of air than on the right, the parcel gets pushed to the right. Pressure gradients create motion, and motion creates density changes. If parcels move toward each other, they crowd and density goes up. If parcels move apart, density goes down, and density changes pressure. In a gas, squeezing the molecules closer increases their collision rate and their tendency to push back. Pressure rises. That loop is the engine of sound. Pressure gradients make motion. Motion makes density changes. Density changes pressure, and the cycle continues as the disturbance marches forward through the medium. Notice what's missing. There's no requirement that air travel from source to ear. What's required is that air can be pushed and can push back, and that neighboring regions are coupled. Now you might ask, why does the disturbance move at a particular speed? Why does sound in air move at around a few hundred meters per second, not 10 meters per second or 10,000? This is where the real sound story becomes surprisingly simple. Sound speed is not mainly about how loud the sound is. It's mainly about two properties of the medium, how stiff it is and how heavy it is in a certain sense. The stiffness is how much extra pressure you get when you compress it a little. Physicists call it something like a bulk modulus in simple cases. You can think of it as springiness. If you squeeze a medium a little and it responds with a big restoring pressure, it's star. In fact, the heaviness is density. How much mass you have to accelerate when you push on a little region. Sound speed is basically springiness divided by heaviness, then take a square root. If the medium is very stiff, a little compression creates a strong restoring force, so the message gets passed along quickly. If the medium is very dense, it takes more effort to accelerate it, so the response is sluggish and the wave travels more slowly. This is why sound travels faster in many solids than in air. Solids are much stiffer. Their atoms are bound in a lattice that resists compression strongly. Even though solids can be denser, stiffness often wins and the wave speed is higher. And it's why helium, a light gas, has a higher speed of sound than air. It's not because helium is more eager. It's because the combination of its stiffness and density yields a higher ratio. The details depend on how pressure responds to compression, which involves thermodynamics, but the intuition remains, springiness and inertia. Now at this point, a textbook often gives you the wave equation or a diagram and moves on. But the title of this video is basically accusing your book of skipping the best part. What is sound really, physically, in a way you can picture? So let's paint the picture you can carry around. Imagine a long line of shopping carts, bumper to bumper, with slightly springy bumpers. You push the first cart forward and then quickly stop. The first cart compresses into the second, and the springiness pushes the second into the third, and so on. A compression travels down the line. But most carts don't end up rolling down the hallway. They each move forward a little, then back a little, transferring the news of your push. That's sound in one dimension. Now imagine not carts but air. The bumpers are pressure forces from collisions. The coupling is the fact that if one region gets compressed, it pushes on the next region. The wave is the propagation of that compression-relaxation pattern. And here's a subtle but critical point. The famous wavy line people draw for sound is not the air's physical path. It's a graph of one of those variables, like pressure or displacement, versus position at a fixed time. If you draw pressure on the vertical axis and position on the horizontal axis, then yes, you get a wave-shaped graph. But that does not mean the air is physically shaped like a snake. It means different positions in space have different pressures at that moment. A useful way to catch yourself is to ask, what's on the vertical axis? If it's pressure, then the height is not height at all. It's how squeezed the air is there. A peak is a compression. A valley is a rarefaction. Nothing is literally up there. If it's displacement, then the air parcels move forward and back. But again, that displacement is along the direction of travel, not perpendicular. The wiggle is in the number, not in the air's shape. So, let's go back to your hand near the speaker. Why no steady wind? Because the particle motion in a sound wave is oscillatory. For a pure tone, it's roughly sinusoidal in time. The air parcel moves toward you, then away from you, then toward you again. Over a full cycle, the average displacement is zero. No net transport of air. But wait, you might object. Sometimes you do feel wind from a speaker. You can put your hand near a subwoofer and feel air moving. Yes, and this is where we must be honest. A speaker can create a little actual flow in certain conditions. For example, if it's in a box with a port, the port can produce jets. Or if the speaker cone is large and moving a lot, there can be nonlinear effects and small net flows or streaming. But that's not sound itself. That's extra fluid motion that can accompany strong sound fields. The normal, everyday idea of sound, what carries a melody across a room, is not a bulk flow. It's alternating pressure and velocity fields. Now let's make another leap that most books hint at but don't make you feel. A sound wave is not a thing. It's a process. It's like a traffic jam wave. Have you ever been on a highway where everything suddenly slows down and then later speeds up and you pass the original cause and there's nothing there? The cars were not the jam. Each driver just braked and then accelerated. The pattern of brake then go traveled backward along the line of cars, even though the cars moved forward. Sound is like that, except in 3 dimensions, in a medium that pushes back elastically. The air molecules are the cars. They oscillate. The pattern moves. Now, if sound is a traveling pattern, what does it carry? It carries energy and information. Energy because compressing air stores potential energy, like a spring. Moving air has kinetic energy. The wave involves both, swapping back and forth as it moves. There's also a flow of energy through space called intensity, information, because the pattern can be shaped. Speech is not just a pure tone, it's an intricate time-varying pattern. Your ear is a pattern detector. And this brings us to another misconception, the idea that sound is a single frequency. If you pluck a guitar string, you don't get one frequency. You get a fundamental plus many overtones, plus a complicated startup transient. If you clap, you get a pulse that contains a wide range of frequencies. A sine wave is special because it's the simplest repeating pattern, but nature doesn't owe you sine waves. So why are sine waves everywhere in physics? Not because the world is made of sine waves, but because sine waves are the easiest patterns for a linear system to handle. If the system is linear, then a sine wave in produces a sine wave out. Same frequency, maybe different amplitude and phase. And any complicated pattern can be expressed as a mixture of sine waves. That's not mysticism. It's just a way of bookkeeping. But it hides the real event. A clap is a pressure kick. Your book might show you its Fourier decomposition, but the physical thing that happened was a localized shove and release that propagated outward. So let's take a pulse seriously. Imagine you have a line of air parcels. At time 0, you push one parcel forward and let go. It compresses its neighbor. That compression region moves, and behind it the parcels have moved a little and then settled back. If you were to plot pressure versus position at successive times, you'd see a bump moving along, not a never-ending sine wave, but a packet. That packet is closer to what most sounds are, finite disturbances, not infinite mathematical waves. Now, if you want to understand what your ear hears, you have to understand something about how sound interacts with time. Your ear is sensitive to frequency, yes, but it also cares about changes in time. The onset of a sound, the transient, is often what tells you what produced it. That's why a piano and a flute playing the same pitch at the same loudness still sound different. The spectrum matters, but so does how it evolves. However, and this is important, that's hearing psychology. The physics is the pressure pattern in the air. The brain is another chapter. We're going to touch it only when it helps, and not confuse it with the wave itself. Now, if you're still uneasy, here's a question that forces clarity. If sound is a pressure pattern, can you see it? You can't see pressure directly with your eyes because your eyes respond to light, not to pressure. But you can sometimes see its effects because pressure variations in air come with density variations, and density variations bend light a little. That's what Schlieren photography exploits. It uses optics to turn tiny density gradients into visible light and dark patterns. When you see footage of a shock wave around a supersonic object, you are literally seeing the density field in air. And that tells you something huge. Sound, even ordinary sound, is a moving field of density and pressure variations. Now, ordinary sound in air has pressure variations that are tiny compared to atmospheric pressure. A normal conversation might be pressure changes of a few millionths to a few thousandths of an atmosphere. That's why you can't see it easily with your naked eye. But it's there. If you generate a strong pressure wave, like a shock from a whip or a bullet, the density gradients become sharp enough that Schlieren makes them obvious. A whip crack isn't just loud. It's a case where parts of the whip move faster than the speed at which pressure information can travel in air, so the pressure wave piles up into a shock. The gentle sine wave approximation breaks, and you get a steep front. That's not a separate phenomenon. It's what happens when the wave's nonlinearity matters. Here's the clean way to think of it. In small amplitude sound, compressions and rarefactions are mild. The wave travels at a speed determined by the medium. The shape of the wave doesn't distort much. In larger amplitude sound, the compressed parts can travel slightly faster than the rarefied parts because in a gas, the local speed of sound depends on local conditions like temperature and compression. That means the front of a compression can catch up to its own back. The wave steepens. Eventually, it forms a shock, a very thin region where pressure and density jump. So when you see a shock wave, don't think a different kind of sound. Think sound pushed beyond the gentle regime. Now, another line of evidence is even more on the nose, acoustic came. RAS. There are arrays of microphones that can map where sound is coming from by measuring tiny time delays and reconstructing the spatial pattern of the pressure field. In some demonstrations, people see sound emanating from a source and reflecting off objects. But notice what's being reconstructed. Not wind, not airflow, but a wave field, phase and amplitude. That's why you can have interference patterns, nodes and antinodes, and standing waves. Standing waves are another point where the textbook picture is both helpful and misleading. A standing wave looks like a wave that isn't traveling. But what does that mean physically? How can something wave and not go anywhere? The physical answer is wonderfully simple. A standing wave is the result of two traveling waves going in opposite directions. Imagine you have a stretched, springy medium. Send a wave to the right. It reflects from a wall and comes back to the left. Now at every point, the medium feels the sum of the two disturbances. If the timing is right, some points are always being pushed and pulled in such a way that their displacement remains near zero. Those are nodes. Other points swing a lot. Those are antinodes. In air, the standing wave involves pressure nodes and antinodes too, depending on the boundary. And now you can understand acoustic levitation. In a strong standing wave, there are stable regions where the pressure field exerts an average force on small objects, trapping them near nodes. That's not magic. It's an effect of how oscillating pressure gradients can produce time-averaged forces. Again, not wind, a pressure field. At this stage, you might be thinking, okay, sound is pressure variations. Fine. But the title promises something your book never showed you, and to deliver that, we need to go one step deeper than pressure wiggles. We need to answer, what exactly is the physical entity called sound at a point in space? If you freeze time and pick a point in the room, sound there is not a traveling thing passing through like a bead on a string. It's a local state of the medium, a certain pressure deviation, a certain particle velocity, a certain density deviation. Those values change with time, influenced by neighboring points through the medium's coupling. In other words, sound is like a field, not the electromagnetic field which can exist in empty space, but a mechanical field that requires matter. A field in the sense that at every point you can assign numbers, pressure fluctuation, velocity. Those numbers tell you what's going on locally, and that's why you can talk about superposition. If two sounds overlap, the pressure deviations add. The medium simultaneously participates in both patterns. The particles don't choose one or the other. They respond to the sum of forces. This is why two speakers can create regions of silence. It's not because the speakers suck sound away. It's because at those points the pressure deviations from the two sources cancel. If you've ever experienced noise-canceling headphones, they're exploiting this. They add a second, so on pattern designed to cancel the first at your ear. It works best at low frequencies because the wave field is predictable over that scale. The physics is simple addition of pressure fields. The engineering is the hard part. Now here's an excellent question that ties everything together. If sound is a field, why does it obey a wave equation? Because the wave equation is what you get when you combine Newton's second law with the medium's elastic response in the small disturbance limit. You don't have to do the full math to feel this. You only need to see the logic chain. Pressure differences create acceleration. That's Newton. Compression creates pressure. That's the material's stiffness. Link acceleration to displacement, displacement to compression, compression to pressure, and you get a relationship where the second time derivative of displacement is proportional to the second space derivative of displacement. That's the wave equation. The constant of proportionality carries the speed squared, and that speed comes from stiffness over density. The reason this is satisfying is that it's not a rule handed down from above. It's a consequence of the medium being made of stuff that resists compression and has inertia. Now let's pull in another dramatic exhibit, the bell in a vacuum. If you put a ringing bell inside a chamber and pump out the air, the sound fades. The bell is still vibrating. The mechanism of the bell is still there. But the medium is gone. No air, no pressure field that can propagate to your ear. The vibrational energy stays in the bell and the apparatus, with only tiny leakage through whatever solid connections remain. This is a simple and powerful reminder. Sound is not vibration in general. Sound is vibration transmitted through a medium as a wave in that medium. In vacuum, the vibration can exist, but it is not sound in the usual sense because there's nothing to carry it to you. Now here's a subtle twist. Sound can travel through solids and liquids too, and sometimes you hear a neighbor through a wall. How does that fit? It fits perfectly if you keep the mechanism first viewpoint. A solid is also an elastic medium with inertia, but its elastic response is different. It can support not only compressional waves but also shear waves, because solids resist shear. That's why earthquakes have different wave types. Air doesn't support shear waves the same way. It slips and flows. So when you hear through a wall, you are hearing the wall carrying vibrational patterns, which then couple back into the air on your side. The wall is acting as the medium for part of the journey. This is why sound insulation isn't just blocking air. It's about breaking coupling pathways, damping vibrations, and avoiding rigid connections that transmit mechanical energy. Now, so far, we have built a coherent picture. Sound is a propagating pattern of pressure and particle velocity in a medium, arising from the medium's elasticity and inertia. But the title says your physics book never showed you what sound really is. So what is the missing revelation? The missing revelation is usual. This. Sound is not primarily about displacement. It is about pressure and momentum. The displacement of air molecules in audible sound is astonishingly small. Even for loud sounds, the back and forth motion of an air molecule might be fractions of a millimeter or less. Often it's far smaller, micrometers or nanometers. The pressure variations are tiny fractions of atmospheric pressure, yet your ear is exquisitely sensitive, and that changes your intuition. You stop imagining dramatic sweeping motions of air. You start imagining a room full of air that is almost perfectly still, except for unimaginably tiny coordinated oscillations of pressure and velocity fields rippling through it. That's sound. And once you see it that way, the weird things make sense. Interference patterns make sense because fields add. Standing waves make sense because two traveling patterns superpose. Acoustic levitation makes sense because oscillating fields can produce stable force landscapes. Shock waves make sense as a breakdown of the small disturbance approximation. The speed of sound makes sense as stiffness versus inertia. Now let's cement this with a simple do-it-in-your-head experiment. Imagine a long hallway full of people standing shoulder to shoulder, facing forward. Each person can lean forward slightly to bump the next person, then lean back. Person 1 leans forward and bumps person 2, who bumps person 3, and so on. A compression moves down the line. At no point does a person walk down the hallway. The people don't travel. The leaning pattern travels. Now add another detail. Suppose someone halfway down starts leaning in a more complicated way. Not just forward, back, but a pattern that encodes a message. That pattern travels to the end. That's speech. The medium doesn't need to transport matter. It needs to transport coordination. Now, if you're wondering what coordination means in physics terms, it means correlation between the motion of neighboring parcels of the medium governed by local forces. And that's why sound is, in a deep sense, one of the best demonstrations of how local laws produce non-local behavior. Every molecule interacts locally. It only bumps its neighbors. Yet from those local collisions emerges a wave that can travel across a stadium carrying a song. Now there's one more layer your book often hides, and it's connected to something Feynman loved, checking the validity of approximations. We've treated air as a continuous fluid, parcels, pressure fields, smooth functions. But air is made of molecules flying around and colliding. When is the smooth wave picture legitimate? It's legitimate when the wavelength is large compared to the typical distance a molecule travels between collisions, the mean free path. In ordinary air at room conditions, the mean free path is tiny compared to audible wavelengths, which are centimeters to meters. That's why the continuum wave picture works so well. But if you go to very low pressures or very high frequencies with extremely short wavelengths, the continuum picture breaks down. The medium can no longer act like a smoothly coupled elastic substance. The message passing by collisions becomes too sparse to support a clean wave. This is the kind of point that makes physics feel honest. We don't just declare an equation true. We say, here's when it works, and here's when it stops. Now, if you want a final conceptual gem, here it is. In the simplest story, sound is the motion of a disturbance through matter. In a more modern language, you can say sound in a solid is quantized as phonons, quanta of vibrational energy in a lattice. That's quantum physics territory, and we don't need it to understand everyday sound. But it's nice because it reinforces the same idea. Sound is not a stream of particles flying from source to listener. It's a mode of organized motion, and at the quantum level, it comes in packets of energy in the vibrational field. And notice how smoothly that idea fits. The field picture isn't a metaphor. It's a way of organizing the physics that stays useful even as you go deeper. So let's tie it all together, because the title promised a replacement for the misleading picture. Sound is a traveling organization of motion, a moving pattern of pressure and momentum that exists in matter the way a ripple exists in a pond, real and measurable, but not made of stuff that goes from A to B. When you hear a voice across a room, you are not catching molecules that left the speaker's mouth. You are sensing tiny oscillations in pressure at your eardrum, caused by a pressure pattern that propagated through the air, parcel by parcel, neighborhood by neighborhood, following Newton's laws. And when you see a wave drawn in a book, you should now automatically ask, what quantity is being graphed? If it's pressure, you're looking at compressions and rarefactions across space. If it's displacement, you're looking at back and forth parcel motion. Either way, the wave shape is a graph of a field, not a literal bending object. The next time you hear music through a wall, picture billions of atoms politely shoving their neighbors, passing along a pattern like a rumor, not like a package. And once you start seeing the world this way, you'll notice something else. Almost everything that travels in physics is like this. Light is a traveling pattern in the electromagnetic field. Radio is too. Water waves are traveling patterns of surface height and motion. Even traffic jams are traveling patterns of driver behavior. Nature loves to move patterns around more than it loves to move objects across a room. So here's a final challenge you can try anywhere. Find a low note on a speaker. Hold a candle flame nearby. Watch it. You won't see the flame pushed steadily one way like wind. You'll see it dance back and forth in time with the sound. That dance is the local signature of a field, pressure and velocity oscillating where you are. That's what sound really is.